Let's start. Welcome Michael Rees. He's a Principal Program Manager at Microsoft. We will have Q&A at the end of the session. Remember that all sessions are recorded. You can find a link to our YouTube channel at the Big Data Virtual Chapter website. Again, it's bigdata.sequelpass.org. So, hello Michael, I'm making you presenter and you can start anytime at this point.
Thanks, Paco, and I hope you can all hear me. It's a pleasure.
Yes, we do hear you. Thank you very much for coming to our virtual chapter.
Yeah, it's great to be back. Some of you might remember that I was presenting on U-SQL back. Let me just hide this quickly, see if I can. Let's see, how do I hide the control panel? No, that's better. So as you might remember, I have been presenting on U-SQL already twice earlier this year. Both of these presentations are on the aforementioned YouTube channel, so you should be able to go and review them if you haven't seen them already, or if you want to recap what I have talked about back then. So just as a quick recap, in part one I did introduce U-SQL, talked a little bit about why we introduced a new big data query language and what it was about, showed the philosophy of U-SQL, that it's basically a combination of SQL for declarativity and C# for extensibility, and demonstrated some of the power and simplicity of U-SQL to query over unstructured data, how easy it is to extend it with C# and assembly, and operate over multiple files. In part two, I then introduced the kind of SQL-ish aspect of U-SQL, starting with the metadata model and U-SQL objects such as U-SQL databases, tables, assemblies, etc. And then showed you how to do some of the SQL aspects with U-SQL, including cross-apply, joining, windowing functions, contrasted it to like the standard SQL experiences, and also talked about data scale-out with partition tables. Today, in part three, I will be focusing on two main capabilities that I consider to be more advanced capabilities. The first one is distributed federated queries with U-SQL, where I show you how we can query data where it lives. And then also I will go into a little bit more advanced extensibility capabilities in U-SQL that allow you to introduce your own user-defined operators and user-defined aggregators, which we then will be executing in the context of U-SQL in a scalable way. And as an outlook, in part four, which will be a session that will be given by Rukmani, a team member of mine, she will be going and showing you more examples of how to use the extensibility capability to basically build up your own libraries that you then can also share with people, and show you some cool use cases of doing special data processing beyond just CSVs using the extensibility framework. So having said that, let's now start. And let's tackle the first topic, which is query data where it lives. One of the important aspects of operating data lake, besides obviously being able to just put your data into the data lake and then use the data according to your needs at a later stage by schematizing it and analyzing it and cleaning it and transforming it, is that as part of that process, you probably already have data, existing data in other locations that you might not want to necessarily go and copy into the data lake, because you still want to continue to use the data in other locations because you have existing pipelines or existing data acquisition systems, etc., that you don't want to go and basically redevelop. So one of the things that we have started adding is the ability to query data beyond just the Azure Data Lake Storage account that you get with your Azure Data Lake Analytics account, but also the ability to query data that lives in other places. In particular, we give you the ability to read and write data that lives in the Azure Windows Azure Blob Store accounts, and we give you the ability to query but not directly write data that lives inside SQL servers inside the Azure data inside the Azure context. So that means normal SQL Server instances inside Azure VMs. It means that you can query Azure SQL databases and you can query Azure SQL Data Warehouse as well. And the reason why we give you these capabilities is that it avoids the necessary data movement that you would have otherwise, and you can get a single view of the data from within U-SQL without necessarily having to worry about where the data actually lives. And not only do we give you that view, but we also will be giving you an execution strategy that will allow you to basically push queries into remote SQL sources. That includes filters, projections, joins, etc. And now let's take a look at the Windows Azure Blob Store first, and then later we will be diving a little bit more into the Federated Queries as well. If we look at Windows Azure Blob Storage, you will be noticing that when we access files in U-SQL, we basically provide you URIs to access them. As a note, all the URIs are always implicitly encrypted channels, so that means even though we are using ADL and WASP as the scheme, they will be basically using encrypted channels and will be encrypting the data during transport. Now, the ways to access these files, you have the ability to write relative URIs that will go to your default associated ADL storage account. But you can also specify absolute URIs to access other ADL storage accounts to which you might have access to by simply getting access granted with AAD. And if you have Windows Azure Blob Store accounts, you can also access the Windows Azure Blob Store account data with U-SQL. Now, the way to do that is that unlike in ADLS, where you basically just have to get permission added to the ADLS storage account, here you actually have to go and register your Windows Azure container and account either through the Azure portal on the Azure Data Lake Analytics or Storage portal, or through corresponding Azure Data Lake PowerShell command. During that registration, you basically give the storage account name and the storage key. We do not yet support shared access keys, and that's something that I think is on the roadmap to be added eventually. Now, once you have access to the Windows Azure Blob Store account, then you can basically do your standard U-SQL processing. Now, why would you want to do that? Well, the reason that we give you access to that is that most of your current big data that you might have managed with HD Insight or with your other tooling in Azure probably currently lives in Windows Azure Blob Store. Now, there is benefit in moving that data over to the Azure Data Lake Storage account in terms of scalability, size of data, etc. But potentially you have existing data pipelines that still need to access the Windows Azure Blob Store account, or you have Azure services such as, for example, Azure SQL Data Warehouse that do not yet support ADLS, and so you want to be able to basically still give them access to the data that you're producing, or you want to have access to the data that they produce to be able to operate it on it with Azure Data Lake. So these are some of the use cases why you want to have WASP. Now, one caveat when writing to WASP is that it is potentially a little bit more of a performance bottleneck because WASP was not designed to be a high-scale big data store originally. One place where this shows is if you have a large output, if you write a large file into WASP, we normally write files in parallel where you have, if they're large enough, which means that you will have individual, what we call extents being written in parallel into the file system. And then at the end, during the finalization stage of the job, these extents are being stitched together. Now in Azure Data Lake Storage, this is a metadata operation, so it should be fairly quick to just update the metadata about that the file consists of these extents. In Windows Azure Blob Store, because the Azure Blob Store doesn't have the same notion, basically writing and stitching these files together is a size of data operation, so it can take a long, long time. So that's why we suggest that if you have to write large files in WASP, that instead you're writing it into a directory where you then use multiple files basically without having them stitched together. So here on the slide you see an example where I say output address to WASP, where I have the file underscore curly brace star curly brace. Now what this means is that when I write files to such a pattern, then I will get one file per output invocation, and the curly brace star curly brace is replaced with a unique GUID. So this is similar to like a little bit what Hive is doing when it writes large data. It will basically write it at the directory level, and then we'll have different extents at the file level. So you can basically mimic that using output if you have to write a lot of data into WASP. So after this conceptual introduction, let me just switch over to Visual Studio and show you some sample code, both for WASP, and then I also switch over to my Federated Query example as well. So let's see, where is my ambulance data set here? So this is the ambulance data set demo that is available on our GitHub site. You can reach the GitHub site from u-sql.io, and by the way, these links are all at the end of the presentation in a resource slide, so you don't have to necessarily remember them. And what I show you here is a slide that does some very simple extraction of some data. Let me quickly highlight this. So what we do here is we have a file that contains driver information. Now, driver information is like the driver ID, the name of the driver, the city, the phone number. So this is like, in this case, it's like the ambulance driver, so to speak. They are stored in a file that if I go up here and resolve these variable names, you will notice this lives inside a WASP container called ambulance demo on my Emry's Kona 2 Windows Azure Blob Store account. And so now I basically use this U-SQL expression just using this WASP account. So it's very similar to how I would access data inside my Azure Data Lake. The only difference is I have a different URI. And then I do my transformation here. In this case, what I do is I basically count the number of drivers that I have per city and per country. And then I take the top 10 here. And I output the result out into my output location. And if I look at the output location up here, you will notice that it again goes against the WASP account. So now I'm writing it back out. So let me just submit this job here. Now, while this is running, let me quickly go how you can actually take a look at this WASP account. If you go in Visual Studio to your Server Explorer, and I go here to my Emry's Kona account, and under the storage accounts, you will notice that I have now, let me zoom in quickly, that I now have not only my default storage account here, but I have associated my Emry's Kona 2 Windows Azure Blob Store account, which has these three containers in it. So now I have access to these 3 containers as well. Now the job is running. Now while it's running, let me go back and talk a little bit more about what I'm doing here in the script. So in this script, I go from WASB to WASB. But of course, you can also have a script that goes against multiple different data. So in this case here, you have a script that again is on the GitHub side that takes the driver data from my WASB location, but it also takes my trip information, like the trips that these drivers do, from my ADLS location. And then I can, inside my script here, I extract from WASB and ADLS, and I am joining, for example, down here, the data. Let's see, down here I have my drivers and my trips, and I basically join them. So I can just combine data coming from these different locations very easily. Oops, let me see. There's a job view here. I think might have lost that one. Let me see over here quickly. Nope, that's not the one. I must have closed it. So let's go quickly and look at my job. Here it has completed. Let me open. The output here, so I can double click, similar to what I do with Azure Data Lake tooling. I can do the same, double click on my WASB account file, and it will be opening it, and it will be previewing it here inside my file. And you can see I have 6 drivers in London, 5 drivers in Mexico, 4 in Sao Paulo, etc., and then 2 in Portland. Looks like Portland is an important place for my ambulance drivers here. So this is how you can query Windows Azure Blobs for data. It's very simple, basically the same way that you do Azure Data Lake Storage. One caveat is when you write, make sure that if the file is big, going basically over multiple output threads, that you are avoiding the stitching together. Now let's go back and look a little bit more about the federated query aspect. For federated query, I also have here inside my ambulance dataset a simple query, and I go here over basically the steps on how to do this. So let me quickly set the scene here. We have in a SQL database that might be, in this case, either a SQL Azure database or an Azure VM running SQL database. That contains dispatch and SQL patients data. Now, that might be because I have, let's say, a dispatch system and a CRM customer or patient management system that is using SQL Server to run that on. And now I want to combine this with some of my Azure Data Lake data where I get the kind of telemetry data in for my ambulance trips, etc. And I want to kind of do some interesting look at how quickly are my patients being reached if there is a dispatch incident or something like that. So what I do here now is when I create a connection to a SQL Server database, I first have to create a credential object. Now, the credentials need to be created using the Azure Data Lake PowerShell command. The reason why that is that we have a problem in not allowing you to have secrets inside USQL scripts, because you might be sharing those USQL scripts inside Azure Data Lake. So therefore, we kind of make you creating your secret, which contains your SQL database password and your database account name, etc. in PowerShell. So you can see here the PowerShell script in this comment, how you would do that by basically adding your subscription ID to set the resource management context, and then you basically convert your password into a secure string, and you create a new secret object. I call this here ambulance DB secret. And then you create a new catalog secret using this Azure Data Lake Analytics PowerShell command. And in this case, I register the secret inside the master database for this database host. And I provide my Data Lake account name, obviously, so that I know which database master I have to go and create it in. Now, once I've done that, I have my password encoded inside my secure secret store service, so to speak, inside the metadata. So now I still, at the moment, have to create my metadata object that represents the secret. And so I have to now, as a second step, create my database secret with a given username and the corresponding identity. I create here two. I create one for the ambulance DB and one for the patient DB. You will notice they have different usernames here and obviously different identities, which are the identities that I've specified up here when I created the secret. Now this is the current step as of June. Before we go into GA, these two steps will be merged into one. So that means that you actually create the credential object through PowerShell, and you will have the credential objects available directly without having to do another DDL statement inside SQL Server, inside U-SQL. So this is kind of the first step. Now the second step is, now that I have the credential, I can go and create my data source abstraction. Now I basically create, for that we have DDL in U-SQL. You say create data source, and then you give it a name, and you say from what type of service do you want to create a data source. So in this case we have Azure SQL DB, and we have SQL Server, which is for SQL Server running on Azure VMs right now. And each one of those data source types, like Azure SQL DB or SQL Server, have their own kind of requirement about what are the options in the with clause that have to be provided. Now in this case, they both, since they're both SQL Server, they kind of have similar look and feel. The first one is you provide the provider string, which contains then the database. You say what trusted connection it is and whether it's encryption or not. And you will notice that Azure SQL DB requires encrypt equals true, while the SQL Server IIS currently only works with encrypt equals false. Then you provide the corresponding credential, which contains the secret. And then the next step is that you say which data types am I okay with to be remoted against. What that means is that obviously SQL Server has a SQL type system. U-SQL has a C# type system. So there are semantic mismatches between them. Like, for example, precision and scale on floats are managed at the type level in SQL Server, but at the instance level in C#. You might have nans and negative infinity, positive infinity in floating and double in C#, but the floats and reals in SQL Server, they do not understand some of these IEEE 754 special values. So you get semantic mismatches. But if you're fine with having some of these semantic mismatches shown up, and we are trying to get as close as possible to like the C# semantics when you remote the queries, you can say, I'm fine with the remote semantics that you get, and I can specify which types expressions are remotable. And so this is basically what I do here with this remotable type. So in this case, I'm saying, well, I'm fine with almost all the types that I can remote. Just send them over. I don't care that my string types might be running case insensitive, for example, in the SQL database, even though C# is case sensitive. So now this is the setup. I've already done that, so I'm not going to run this right now. And now I can start running my federated queries over. So let's take a look at a simple federated query first. What I do here is I show you a little bit what are the different ways of interacting with my remote data source. The first thing is I can just query directly my remote data source, where I basically just say in the from class, read from this external data source and read from this location object. Now this location object has to be a row set, so it has to be a table or a view primarily. And then I can just say what is my U-SQL expression here. So in this case, I have a couple of expressions here, like I do a group by in this case. And then I output the result into my Azure Data Lake storage account for further investigation. So this is a very simple way. What I do here is I don't actually have to know a priori what my metadata objects are in SQL Server. I just can access anyone that I like. There is a default mapping going on, obviously, for any of those types into the C# type system, where it basically chooses the closest type that it can find to represent whatever is over there. Now, additionally, if I want to kind of make the objects discoverable in my U-SQL metadata catalog, I can create external tables. Now, I don't have to, as you have seen earlier, but it definitely helps me with two things. One is I can specify the exact C# types that I want to expose. So at that point in time, I basically kind of assert that, for example, customer key is a not nullable int, while a pnation key is a nullable int. And I give you the location here. And then I basically do the same query as above and output that as well. So these are basically both giving me the same results, one time directly querying against the table, one time querying through the external table. So let me submit this job, and while it's running, I actually can bring up a previous job that I run to do so. So this is the job that I ran earlier today. And you notice it says here empty input. Oops, let me go back here. The empty input basically is just because there is no Azure Data Lake Storage input. There's no file input. We are basically talking directly in the extract node. I open this here quickly. So you will notice here there's a SQL proxy native extractor here that we are calling, which is basically our connector to the remote data source, and which then will be pushing the queries through to give me back just the data that I basically requested. And it then runs. You can see both of them run in about 5 seconds. They run obviously in parallel because they are both accessing the same source data in the remote SQL database, but otherwise they are basically doing the same thing. And if I double click on the result here, just to show you what the result is, you will notice now here basically the patient ID, the information, I think whether it was alive or not still, and some other information here that I got from the schema. Let's go back to the job here. Let's quickly close some windows that we are. So yeah, so I looked at whether the nation key, if the person is alive, and how many patients I have inside the nation per alive or death status, basically. So this is a simple way of doing evaluation. If I add predicates on it, then obviously the predicates will be pushed over. So let me show you a more complex example here. So in this case, what I do is I basically now get my vehicle information from my U-SQL table. So this is a U-SQL table that I have inside my U-SQL metadata service. So this lives not in a SQL database. That contains vehicle information such as when the vehicle drove, at what average speed, at what speed, etc. And I do some grouping here on this. Then I create an external table on the SQL Patients database on my SQL Patients and also on the dispatches. They are both inside the same database here. And then I do a three-way join. Now what I do in the first join here is I look at which patients I have dispatches for. So this is a join that I specify in U-SQL, but it goes against two tables living inside a SQL database. And then I take the result of that join and join it with my vehicle information that I got from my Azure Data Lake Store. And then I write the output. Now again, I executed that job a little bit earlier today, and the script looks like this. Let me quickly zoom in here a little bit. So you will notice here is my vehicle GPS that I operated on. But you notice here there's only one input here, even though I have two input files. Why is that represented this way? Well, the reason is that I'm actually combining the join, and since it goes against the same data source, I am pushing the type of the predicate where I do the join on, so the join predicate is a remotable type. I can now push the join into my SQL database. So I'm only getting a single vertex here as an input because my extraction on that, so to speak, my federated query actually executes the join remotely inside that SQL database. And so I'm getting back my joined SQL table here, and then I basically do my join down here between the result of the join inside the SQL Server database together with my vehicle GPS to get my ambulance incident data that I want to analyze further. So this is showing you kind of the power of the federated queries. It actually not only like pushes simple projections, but it pushes filters and it pushes even joins if it can, based on your assurance that you are fine with the remotable semantics. So let me go back to the presentation and kind of summarize. So federated queries basically give you the ability to minimize data proliferation in many different locations. You can query the data where it lives. You can use U-SQL over all Azure data, be it WASP, be it SQL Azure, be it U-SQL data itself. And we will be giving you efficient and reliable execution strategies using our framework that we use for executing U-SQL. And we are trying to be as close to the semantic equivalence in those heterogeneous data type environments as possible, and give you the option of basically choosing whether the predicate is remoted or whether it's being executed locally. You also have the design choice between doing schema-less design, where you can do fast time to query, you can do exploratory analysis. You don't have to create a metadata object, so your database administrator might be happy on the U-SQL side that you're not creating external tables because you're just doing some exploration. Or you can decide that you want to have a schematized design, which then gives you a guaranteed schema that you expose over the data source, and it gives you the basically ability to make the object discoverable inside your U-SQL context as well. And then, as I mentioned, we have the advanced federated query capabilities with some optimizations and the ability of pushing predicates and other expressions over. Just to summarize, you have to first create your credential management. Today it's done in 2 steps, one in PowerShell, one in script. By the time we go into GA, you will only have to do it in PowerShell to create the credential object. Then you basically create the external data source on Azure SQL Data Warehouse, SQL DB, or SQL Server in Azure VM. And at the end, you have the ability, optionally, to schematize your design. Now, one additional comment I would like to make here is you will have to explicitly whitelist a range of internal IP addresses for your SQL database or SQL Data Warehouse or Azure VM, so that U-SQL can access your SQL Data Warehouse. So you have to make sure that these internal ranges are actually enabled. The reason why this is not done automatically yet is that we are running on a different infrastructure than the standard Azure infrastructure, and Azure hasn't been able to whitelist them automatically yet. We are working on that, but unfortunately I don't have an ETA from when you basically don't have to do that step anymore right now. So Federated Queries, you have to have the scripts in a different script from creating your data sources, but you can create your external tables in the same script. You have the ability to do the pass-through queries, which I didn't show you an example of, except for now, where you basically can say select star from external, so similar to like with the location, except for that this time you actually execute a T-SQL query against your remote data source. So this gives you a lot of flexibility of like running queries against your external data sources, even if you can't necessarily have a view or a table there. Note, however, it has to result in a row set, so you can't invoke store procedures. Then the schema-less design is basically just as I mentioned earlier with the location indication in the from clause, or you basically query directly from your external tables directly. So you can basically, you have master.dbo SQL patients, which is your local instance, and you can query from that. The execution is trying to give you SQL semantics, which means that, for example, we are translating SQL statements normally into it being case sensitive on string data types, etc. But as I mentioned, sometimes if you push things, if we can't enforce, for example, the resolution on a float, the precision on a float to be exactly the same as in C#, so you might get slightly different results when you do the predicate pushing. So now I would like to switch over from my covering of U-SQL with Federated Query and go a little bit more into built-in operators, functions, and aggregators. So we already talked about in an earlier presentation about how you can extend U-SQL very easily with C# expressions. And we have shown you examples using C# expressions directly inside select. When we did the tweet example extraction, we showed you user-defined functions that allow you to abstract these expressions and share them through assemblies with other users of your Azure Data Lake account. And now today I would like to kind of go and give you a quick overview over user-defined aggregators and user-defined operators and show you one example of a user-defined operator. So what are user-defined operators directly? Well, they are the user-defined extractors, outputters, processors, appliers, combiners. So these are basically row set generating and or row set consuming operations that you can add to extend the language with, and reducers, etc. Now, you call them with explicit U-SQL syntax that takes the UDO instance and then basically scales them out over the amount of data and over your execution fabric that you have. So that means you can write an extractor in a certain way to extract, for example, your own data format from your own files, create a row set, and you can choose to have that done either in parallel or on a one file per node basis, and we will be scaling that out using those extract and process and combine and reduce, etc., and cross-apply methods. So here are some tips and warnings, though, both for UDOs and also user-defined types. One, in order to be able to still give the optimizer the ability to push predicates and column pruning through the UDOs, you should be using read-only and required clauses. You should also use pre-sort if you want to have, for example, ordered reducers or ordered aggregators in that sense. Now, in most cases, you don't need to write UDOs. It's okay, and it's actually more performant often to, for example, use selects with UDFs instead of processors. It's normally better to use user-defined aggregators instead of reducers. It's normally better to use cross-apply and hint cardinalities if it chooses the wrong plans than using, again, a processor or a reducer. Also, many of the things that you might want to use a reducer or a processor for, you can actually use built-in capabilities like, for example, the windowing functions, the overexpressions. You can also use SQL.map and SQL.array types instead of the built-in C# dictionary and array types because they are more efficiently supported by USQL. Now, why did we introduce those special cases? Well, there are a couple of things that you can't do with any of the solutions that I just mentioned. So, for example, if you dynamically need to access the input and output to do things, like, for example, you create a JSON document for the data in the row where the columns are not known a priori, where your UDF-based solution creates too much memory pressure, for example, and you can write your code more efficiently regarding memory inside a UDO. If you want to do ordered aggregation, for example, or aggregations where you need to see more than potentially what you can see otherwise using a user-defined aggregator. You need to be able to basically write your own code, and so that's what this is for. Now, what are UDFs? We already talked about that. These are the scalar functions, and UDX are user-defined aggregators. Unlike SQL Server, they are called by a special syntax where we have a keyword called agg that then takes basically the aggregator function as an argument. The reason why we introduced this additional syntax is that it allows us to templatize user-defined aggregators. So you can have user-defined aggregators that are type polymorphic, for example. And I will show you a quick example in an upcoming slide. Now, all of these, the UDFs, the UDX, and the UDOs, must be provided by a referenced assembly. So you will have to have these functions either in code behind or registered inside an assembly. And for that, you can take a look at like the earlier presentations, the first one that I gave on how to do that. So let me show you USQL UDO. There are a couple of samples in the ambulance set. Given that we are getting close to the end, I will focus on a UDO example, a custom reducer that I wrote in response of a Stack Overflow problem. You can see the whole write-up of how I actually designed the UDO and some of the design decisions and why I did what I did in my blog that is referenced down here. And so let's go over and take a look at the code that's in another project here. So let me open that other project quickly. If for some reason this is not cooperating as nicely as I wished, go here and open a recent project. So the actual customer issue was that the customer had a file that contained basically a begin and an end range for each user. Think of it as, for example, let me increase that font size quickly to 200%. So basically the input data has a date begin, a date end, and some identifier, user identifier. Think of it, for example, a log file where a user interacts with, for example, a job service where he submits the job and ends the job, or a time when a user is engaging, for example, with, let's say, my TV show. Now, this log range file actually contains potentially overlapping ranges for each user by the way of how it's kind of measuring interaction. So what I want to do is now I want to reduce and merge overlapping ranges for each user. Now, one way of doing that would be to think first of using a user-defined aggregator. But user-defined aggregators don't give me the ability to basically kind of overlap recursively these ranges in an efficient way. And actually the best way to do it is that I order the data first on the begin date, and then I can basically do it in a streaming way over that, and just look at whether the new begin is still within the range, etc., and do that. So, but we don't have ordered aggregators in U-SQL yet, so the only solution for that is that I write a reducer. So what I have here is in my next step after the extraction here, is that I reduce now my row set by pre-sorting it based on the begin date, and I basically do the aggregation on a per user basis. The output is the same as the input, and that's important for me because that allows me to define what we call a recursive reducer. One of the requirements there is that the input schema is the same as the output schema. I also indicate here that I actually do not do anything with the user column inside my reducer. That's just my partition key here that I just passed through. So I say this is a read-only column, which allows me to then, for example, if I would have a predicate down here, it would allow me to push the predicate through the reducer and put it onto the extractor, which is a very useful performance feature. And then I just output my reduced ranges here to my result file. So let me submit this quickly against my Azure Data Lake account here. And while it's submitted, I'm taking a look at this range reducer here. Okay, the place to see that is in the script behind here, over here in my solution. I basically placed the reducer definition into my script.usql. And so let me increase the font size here and take you quickly through the code. So basically in this case, I only have my range reducer here, which is an implementation of the iReducer interface. And I mark this reducer as a recursive reducer. What this means is that instead of having to have all the data for each partition in a vertex all at the same time, I can split the really large partitions. If I have data skew, for example, let's say one user is very active and has a lot of data, and many other users don't. It gives me the ability to basically scale out my reducer better because now it doesn't have this like single big vertex that dominates the execution. Now I can split it into multiple recursive invocation. Now that means, of course, that the reducer has to be both commutative and associative. So that means that I can basically do that composition. So, for example, a plus can be done recursively, some reduction. But if I do something like, for example, an average, then that per se, the average operation is not. I would have to decompose it into count and the sum, basically. So now, in my implementation down here, it's a very simple implementation in this case. So I assume that the data is ordered. So that means that I can basically now loop over my rows. Each reducer will only see rows for the partition key. So in this case, I only see my input rows for each one of the users. I don't see any other users' data. And now in here, I basically check just if my first row is given, then I basically set my begin and my end date based on the row data. So there's row get date time begin and row get time end. And then if my end is less than the begin, I fix it up just to make sure that I basically deal with intervals that go over end of day scenario. And otherwise, if my row is not the first row, I just loop through it, and then I check if my new begin date is still before my, oops, that's down here. If my new begin date is still inside the interval, I just add to the interval and make it longer by setting the new end date. And otherwise, now I output my previous interval and start a new interval with my inside my step. And then, of course, at the end, I will have one interval that I will have to output at the end. And that's basically all that this reducer does. Very simple C# code. Let's take a look at the, oops, I got an error message here. I guess I haven't uploaded the sample data into my store account. So let me see if I can run this locally here. I think I have the data local. So let's submit it again. That should go a little bit quicker because it's a local execution. No, not at the moment. Let's see. Oh, so for some reasons my input data currently is not available. I apologize for that. I should have made sure that this is the case. But I think we have now time to basically wrap up and then take some questions. And as I said, the sample data and the script are both on our GitHub site as well. And the blog that I mentioned here has a blog post about how I developed this and how I made the decisions, and go into more detail as well. So just to kind of go over the UDO model again, you have basically an extractor or a reducer or an outputter interface that you implement. You can define a non-default constructor if you want to pass in additional parameters to your UDO. And then you basically implement the UDO using a simple UDO model. In this slide here you see how you would do a row-based extractor, for example. So you mark the UDO as a UDO as well. You can add additional options to it, such as the recursive reducer that you saw, or if an extractor has to be atomic on a file, or it can be parallelized. You can do the parameterization of the UDO. You have the UDO signature, and then you basically have the UDO specific processing pattern. In this case, you saw a reducer earlier. In this case, you see the extractor row processor model. Also, you have access both in the input and on the output side to the schemas that are provided. So you can look at the schema to find out what are the data types, what are the names, etc. So you can actually write very generic processors and UDO models as well if you don't want to depend upon a column name, for example. And you can obviously set the result either by name or by position. On the user-defined aggregator model, you basically implement three classes. You implement the aggregation interface. The aggregation interface is always parameterized by the type. The first type is normally the argument type, and the last type is the result type. So in this case, I do basically a sum. And then you basically have, you implement init, accumulate, and terminate. That's it. You can also have multiple arguments. So in this case, I have an accumulation that does accumulate a string and a long, and then results in an int. You can have generic aggregators. That's basically what I mentioned earlier. So you can genericize the argument types. And then the invocation is just done basically by calling out to this aggregator with the parameters using the AGG kind of keyword here. So let me summarize here. You have additional links for UDO expressions and output statements on MSDN to the documentation. The UDO Programmer's Guide is under development, should be available by GA. I apologize for the delay on that. There's additional performance tuning tips for working with UDOs in the USQL performance presentation, but you have the link here. There are some sample projects down here, plus the additional sample project that you can reach from my blog. There's additional links to the different community resources, GitHub site, blogs, etc., and additional documentation to articles and slides. Thank you for your attention, and I think we still have a few minutes for